Okay, good morning, everybody. This is the Bayesian Data Science by Simulation session. We are using AirMeet for the first time. And so hopefully everything goes well here. Hugo is all queued up. So I will just let him get started and then bow myself out of the conversation. So Hugo.
Thank you so much, Mike, both for the introduction, the warm welcome, and hi, everyone, and for all the work you and the team have done in putting this wonderful conference together again. And I'd just like to thank everyone who puts all the hard work into SciPy for putting all the work in to make this happen, particularly when it's not as straightforward to do this online, and they're doing a fantastic job. Hi, everyone, welcome. I see a lot of people in the chat saying hi. That's awesome. Maybe you could just say a bit about where you're calling in from, what your interest in Bayesian data science is, or simulation, or Python, or that type of stuff. Be cool to get to know you a bit. That's awesome. A bit about me. My name's Hugo Bown-Anderson. I work in data science, infrastructure, tooling, developer relations, evangelism-y type stuff, and education. I currently work at a company called Coiled, where we build scalable data science solutions for data scientists based around the PyData ecosystem and SciPy, and based around Dask as well. So check out coiled.io if you're interested. We've got people calling in from all over the place, which is great. I do just want to flag that I am calling in from Sydney, Australia. So it is actually midnight for me. This tutorial is scheduled for midnight to 4 a.m. There are a bunch of exercises to be done in it, which we're going to spread out throughout the tutorial. But there is a chance that around 3 a.m. My energy levels may wane, and I might leave some exercises to do after the fact. But I'll be online when I wake up to answer them as well. Okay, so I've actually pinned in the Slack channel the GitHub repository that we'll be using, that I hope was circulated beforehand. I'm also going to post it in the chat here. I'm not certain how to pin that. Let's see if I can. No pinning. But go to that repository. That would be fantastic. And what we're going to do, if you've downloaded the repository already, if you pulled it, that's fantastic. Otherwise, I'm going to get you to launch the binder here. Okay. Now, binder. Big shout out to Binder specifically, but also more generally Project Jupyter. But Binder provides it's essentially a deployment as a service type thing where I've got a repository here with a whole bunch of requirements, and in terms of the Python packages we need to run this, and Binder sets it up so you can at one click spin up a bunch of computation in order to run the code in this repository. So I'm going to right click on that, and we see that starting. So if you want to run the code in Binder, please do so. Otherwise, you'll be doing it locally, and otherwise you'll be coding along, or just reading along as I'm just reading some of the comments. Okay, we're doing well here. There's a chat tab. There's a Q&A. Oh, great. Thanks, Mike, for posting it in the Q&A as well. Okay, this is fantastic. We've got people from all over the place doing all types of interesting work, and interested in Bayesian stuff as well. And we've got nearly 150 people here, which is super exciting. So without further ado, I would love for us to jump in. So let's do it. The first thing I want us to do is before we actually discuss anything, I just want us to do some imports. So this is incredibly important. I've just opened a Jupyter notebook and I didn't tell you where it is. It says it in the repository, so I made an assumption there. But if you go to notebooks and then go to SciPy 2021, there are instructor notebooks and student notebooks. we're all going to open the student notebooks together. The instructor notebooks have the solutions. So please don't look at them unless you really get stuck when we're doing a hands-on exercise, okay? Great. So let's go to the first student notebook, 01 student, probability, a simulated introduction, and import the packages. Just want to say a bit about the learning objectives of this first notebook and first part of this tutorial. So what we really want to do is understand a bit about what probability means in both Bayesian and frequentist terms. We want to start to kind of build our muscles of simulating probability distributions that model real world phenomena. We also want to understand how probability distributions relate to data generating stories, okay? So thinking about if we have a probability distribution, what type of things happen in the world that give rise to these distributions? And if you've worked with this type of stuff before, you may be thinking about generative models as well, and that's along the right lines. Then we want to think a bit about joint probabilities and conditional probabilities. After that, we're going to get into Bayes' theorem and see why and how and where it's useful. And in the second half of this workshop, we're going to see Bayesian inference in action using probabilistic programming and PyMC3 in particular. So before jumping into starting some simulation, I just want to say a bit about probability, okay? So back in the day, to the pioneers, as I've written here, this is from a great book by Sivyer and Skilling called Data Analysis, a Bayesian Tutorial. Sivyer and Skilling write that back in the day, a probability represented a degree of belief or plausibility, how much you thought something was true based on evidence, okay? Now, this seemed to a lot of quantitative thinkers a bit too vague and subjective. So what they then did is redefine probability as the long-run relative frequency with which an event occurred if you repeated it many, many times in experiments, okay? So the first way to think about it will turn out to be Bayesian of some sort. And the second way of the long-run relative frequency is frequentist. And you can remember that because it's the long-run relative frequency, right? Now, since frequencies can be measured, probability was seen as an objective tool for dealing with random phenomena, okay? So what type of random phenomena are we talking about here? For example, a modern case of this, which probably occupies far too much time of far too many people, but it's instructive to think about, is click-through rate on a website. So knowing that a website has a click-through rate of, let's say, 10%, 1 in 10 people click through, we can calculate the probability of having 10 people, 9 people, 8 people, and so on, click through upon drawing 10 people randomly from the population, okay? So that's the type of random phenomena, for example, we're talking about. And we'll see many more examples as we go on here. So this is interesting, right? Knowing the click-through rate, we can calculate the probability. But given the data of how many people click through, how do we calculate the click-through rate? And how certain can we be of this click-through rate? So one thing that I find very interesting here is that science mostly asks questions of the second form. Given data, what can we say about the world? What can we say about our models of the world? How likely are certain things to be the case, right? So science mostly asks questions of the second form, but we kind of can calculate answers to the first question better. So there's a kind of an interesting paradox here, okay? So we just have a question in the chat saying, what n would you consider to start being reliable for frequentist? It totally depends on what the data generating process is. And we're going to see many examples of this. And we're going to calculate that specifically in a lot of cases. So as I said, science asks questions of the second form, but we know how to answer questions of the first form, which is interesting. And one thing I love about Bayesian thinking, and one of the reasons I really enjoy talking about this stuff, is Bayesian thinking provides a really cool framework for answering these types of questions. And it gives us a way from moving from the probability of the data giving the model to the probability of the model given the data, okay? So we're first going to jump in and explore questions of this first type using simulation. Knowing the model, knowing that a website has a click-through rate of 10%, what's the probability of seeing certain data, such as having 10 people, 9 people, 8 people, and so on, click on through. So let's jump in, people. So let's say a website, I'm just going to have a sip of water. Let's say that a website has a click-through rate of 50%. So 1 in 2, 50 and 100 people click through. So if we picked 1,000 people at random from this population, how likely would it be to find that a certain number of people click? So we can simulate this using NumPy's random number generator. Now, we're not going to do this immediately. The first thing we're going to do is we're going to use NumPy's np.random.rand to randomly select floats between 0 and 1, okay? Because we're just randomly selecting any floats with equal probability, this is known as the uniform distribution, okay? So the first thing we're going to do is to do that and plot the histogram, okay? So remember up above, we imported NumPy as NP, as is standard. So we said, we assigned to X, np.random.rand, and we're going to draw 1,000 samples from it. And then we're going to plot a histogram as so. I'm going to execute this cell and look at that. In the histogram, on the x-axis, it tells us our values between 0 and 1. We have bins of with 0.1 each. See, it's pretty uniform. There are fluctuations due to the random sampling process, okay? So that hasn't really answered our question, though. So we want to sample from a population of people visiting a website, 50% of whom click through, okay? And now we want to simulate what happens when 1,000 people click through. How can we use this to do that? The way we do it is each one of these random choices, we're going to consider a person going to the website, and remember they're assigned a float between 0 and 1. Now we want to simulate half of them clicking through and half not. So what we can do is for each one, if the value assigned to them was over 0.5, we can say they didn't click. And if it's less than or equal to 0.5, we can say they did click, okay? So now, how do we compute how many people click? We have this X, where are all these draws, and we want to say they clicked if it's less than or equal to 0.5. So to the variable clicks, we assign the value X is less than or equal to 0.5. And remember, this is a NumPy array. So what this will actually give us here is an array of true or false values, depending on whether each value was less than or greater than or equal to 0.5. So it'll give us an array of Booleans, and you can verify that. Now, to get the actual number of clicks, remember, true is associated with 1 and false with 0, so we can sum up the array of Booleans. So I'm going to sum clicks. Now, let's think about what we're expecting to see. Okay, so we've drawn 1,000 and the click-through rate is 0.5. So would you expect, if this was hitting the nail right on the head, to get 500, right? But because we're randomly sampling from the population, we should expect something around 500, but we're not quite sure what it would be yet, okay? Okay, and that's what I got, 477, which is kind of close to 500. Great, David got 502. And the other thing to note, everyone, there is a Slack channel called Tutorial Bayesian Data Science by Simulation. And I actually, look, we can use the chat in here. Oh, someone got 500, brilliant. And 2 people got 502, which is spooky because we're all working on different systems and that type of stuff. We shouldn't necessarily expect to get the same number as the person next to us. But with enough people, you will. I'm almost tempted to direct us all to the Slack channel, because this chat, I mean, we can use threading on the Slack channel. Okay, okay, no, this is fine for the time being. If it becomes overwhelming, we can move to the Slack channel. Great, Kyle had a great point. We will get the same result if we set the seed. And this is jumping a bit ahead, but all I want to say there, and we'll get to this, is that what you can do, this is pseudo-random number generation, right? Where essentially NumPy uses a highly sophisticated algorithm to generate numbers that look random, and for nearly all intents and purposes are. But the thing is, it starts with a seed in order to generate these random numbers. And if you and I were to set the same seed, and we'll do that in a minute, we start to get the same results, and that is key for reproducibility in simulation and scientific research more generally. Great. Okay, so if we want to do the proportion of people who click through, so we had the number of clicks, right? Well, over how many people there were, which we know is 1,000, but we want to we don't necessarily want to hard code that into it. Okay, so the proportion who clicked was nearly 0.5. Notice we're doing something with f strings here. If you haven't seen f strings, they're awesome. One of my favorite features of Python 3.6 when it came out. I see Carol Willing. She could probably tell me if it was 3.6. So we already answered this question. Did you get the same answer as your neighbor? If you did, why? If not, why not? And you probably didn't, okay? Because we have 150 people chatting, we see a bit of correlation there, but most people would have got slightly different responses. But you can actually imagine, let's say, this is a really good question. The question I'm about to ask is a really good question. Let's say you had, all you had was the data and you wanted to figure out the click-through rate. What would your estimate be? Now, my estimate wouldn't be 0.5 because all I have is the data. My estimate would be this proportion. And that's actually the maximum likelihood estimate, among other things. Another question is, how confident would you be of your estimate? And we don't know that yet. And Bayesian thinking will provide us a really nice way for thinking about confidence intervals and even the entire distribution of possibilities for the click-through rate here. Now, one way to think about why some people got the same answer is, let's say that most answers will lie between 450 and 550. Okay, that's 100 or 101 possibilities, and we've got 150 people here. So if most answers will be on the order of, out of 100 possibilities, you have 150 people getting them, you're going to get a few people getting the same ones. Okay, you can figure out what's the likelihood of getting 3 people getting the same ones. Okay. I also just want to make clear that we've described probability in 2 ways. We haven't described it mathematically, and we're not going to do it rigorously here because I think it's far more instructive at this stage to go through very intuitive examples. But what we will say is that probability defines a function from a space of possibilities. In the above, it was the interval 0, 1. That describes how likely it is to get a particular point or region in that space. And if you want to go into some of the mathematics, check out Mike Bedencourt's elegant introduction to probability theory for scientists and engineers. So now we're going to take 5 minutes or so to have a hands-on where I would like you all to use random sampling to simulate how many people click when the click-through rate is 0.7. We did 0.5 now. So how many clicks and what proportion of people, okay? So, yeah, take 3 to 5 minutes to do that. while you're doing that, I will actually I would like to take some of the chat, because what I'd like to do is I'm going to post the question in the Slack channel. Give me a thumbs up, a +1, when you've completed the exercise. As an emoji, and I'm going to put one there. If you are able to join Slack, that would be fantastic. I'll still get some signal. There are 62 people in the Slack channel, 150 people here. If there's enough intersection there, I'll get some signal on when people have done it. But if you have the Slack invite, I would very much welcome you in the Slack channel, tutorial Bayesian data science by simulation. Yep, so there's a question, isn't Slack the Slack is called SciPy 2021, and the channel is tutorial Bayesian data science by simulation. Now, if for some reason you can't get access to the Slack channel, you will not miss out. I can guarantee that here. And Babak, yes, it is a channel inside SciPy 2021.
And also, just to let people know, if you can't get to the Slack, there is a Q&A tab in here, and so we can I can monitor that and then bring those questions to Hugo's attention when he takes a break like he is right now.
Beautiful. Thanks so much, Mike. All right, so we have a bunch of people who've completed it, which is awesome. So if the click-through rate is 0.7, then clicks, it's going to be kind of the same. I'm going to do something a little funky and just paste my code here, and it's going to be less than or equal to 0.7. And similarly, I can... Yes, and I actually, so let's execute that. And actually, yeah, because I didn't print, I'll do it anyway, but great. So the number of clicks was 682, and the proportion who clicked was 0.682, okay? Now, this model is known as the biased coin flip, okay? And you may have heard this term before. And essentially, there's a joke here that there are barely any biased coins, so why do we actually use a biased coin flip? And we'll get to that. The whole point is that the biased coin flip actually models, a significant number of real-world phenomena, essentially, or it can be helpful to model. The reason it's called the biased coin flip is because in the 0.5 case, click-through or not is 0.5 chance each. That's just like flipping a coin. 50% chance, half the time it's heads, half the time it's tails. If clicking through is 70% likely and 30% not clicking through, then that's like a coin flip where heads is 70% likely and tails is 30% likely, okay? So that's why it's called a biased coin flip. Now, I asked a question here, can it be used to model other phenomena? And the answer is it definitely can. And we'll see a variety of phenomena it can be used to model. But one example, which of course is highly relevant at the moment, is in infectious disease. It can be used to model whether somebody is infected or not. It can also be used to model vaccine efficacy, among other things, okay? Whether someone is totally protected or not, okay? And we'll see these as we go on. So what we can also do is we can start to think about these types of proportions with real world data. And we'll see more of this as we go through, but I wanted to give a little teaser here, okay? So we'll be using a data set of finch beak measurements from the Galapagos Islands, which are in Data Dryad. There's a hyperlink there. So we're going to import the data, read it in as a CSV, as a data frame, and plot the first 5 rows. So band isn't really interesting to us at the moment. We have a species column, we have a beak length, and a beak depth column as well, okay? So the first thing I want to do is just store the beak lengths in a pandas series. Now, a common question you might have is you want to know what proportion of birds have a particular characteristic. For example, a beak length greater than 10, okay? So how do we calculate that? So really what we want to do is look at, we want to be able to spell first, and then we want to look at the lengths greater than 10. This, as we saw before, will give us an array of booleans to see how many of those satisfy. Remember, true can be thought of as 1, false as 0. We can take the sum of all of these, and what we really want to do then is divide this by how many data points there are. So the length of the panda series here. Okay, so around 85% of birds have beak length greater than 10, okay, in your empirical data. And what have I written there? This is the proportion of birds that have beak length greater than 10, not the probability that any bird drawn from the population will have beak length greater than 10. That's very important to recognize, that this is a proportion in the data set, which is really a proxy for probability. Okay, so and that's what I've written here. As stated above, we've calculated a proportion, not a probability. Okay, so if we want to think about probability, how do we do that? Okay, so as a proxy for the probability, we can simulate drawing random samples with replacement from the data and seeing how many lengths are greater than 10 and calculating that proportion. So what we're going to do is we're going to draw 10,000 samples, okay? And remember we did np.random.rand before? To do it now, we're going to do np.random.choice because we're choosing from a particular data set. We're choosing from lengths. Then the second positional argument is the number of samples, okay? Now, we want to do it with a replacement. When we choose one, we want to throw it back in, okay? And so we're going to have replace equal true here. Now, this is going to be all our new samples. Remember, now we just do what we did above, okay? So we want to know how many of these is greater than 10, okay? We want to sum that up to get the total number, and then we want to divide that by the total number, which is of samples, which is n samples, okay? And we'll see that once again, it's around 85. It's slightly less, could be slightly more, but in this case, it's slightly less. Now, the cool thing about doing this is we can actually look at the distribution and see all the different samples here. We're not going to do that now, but we've actually generated a relatively large data set here now. So I just wanted to go through that because that's something that will crop up time and time again. So now we're really getting places. Edward Kruger has a good question. Look, we'll get there, Edward. Essentially, we have resampled the whole data set. I see what you mean. Yeah, definitely. If you want to get the distribution, Edward's suggestion, if I understand it correctly, is to, I wouldn't say it would be better to do that. I think that's doing something slightly different. But yeah, to resample the entire data set, do that 10,000 times and then take the mean. But essentially, Edward, you'll notice that if we do that, that's kind of similar to it's exactly the same, I think. This is a mean, right? It's the sum over the number of samples. So it'll be the same as, your suggestion would be the same as multiplying this number by the total number or something along those lines. So Luca, you have a fantastic question. Yeah, because what we're trying to do is sample the entire population, and this is actually referred to as bootstrapping. So we're assuming, we're not assuming a lot, but there is a kind of an assumption that the data set we have is representative of the population, so that when we sample it a lot, this is a proxy for the population. But I wouldn't necessarily get hung up on this, and definitely we'll be doing more bootstrapping and definitely looking into it more if you're interested. So I want to discuss another way to simulate coin flips. So in the above, we've used the uniform distribution to sample from biased coin flips. Now I want to introduce another distribution, and this is going to be a trend. We're going to be introducing more and more distributions as we go on. I want to introduce you to another distribution, the binomial distribution. It has two parameters, n and p. Yes, two parameters, n and p, and the binomial distribution is defined as the probability distribution of the number of heads seen when flipping a coin n times when p of heads is equal to p, okay? So it's the number of heads you see when flipping a coin n times when p of heads is equal to p, and there's an extra with here that I want to okay, so this distribution, essentially, I'm not describing it really mathematically yet, but it tells the story of a general model in the following sense, okay? So if we believe that the underlying process generating the observed data has a binary outcome, so affected by disease or not, head or not, 0 or 1, click-through or not, and that one of the two outcomes occurs with probability p, then the probability of seeing a particular outcome is given by the binomial distribution with parameters n and p, okay? So I want to make clear that this is incredibly general. If we believe that the underlying process, and once again, it's amazing how many typos you find even when you've got them all. If you believe that the process underlying generating your data has a binary outcome, and that one of the two outcomes occurs with a certain probability, then the probability of seeing an outcome is given by this binomial distribution with parameters n and p, okay? And any process that matches this coin flip story is a binomial process. You'll also see coin flips referred to as Bernoulli trials in the literature. So what that means is we can also formulate the story of the binomial distribution as the number R of successes in n Bernoulli trials with probability P of success. And this is binomially distributed, okay? So now what we're going to do is use the binomial distribution to answer the same question as above. So if P of heads is equal to 0.7 and you flip the coin 10 times, how many heads will come up? So it's the same model, slightly different question. I correct myself, okay? So the first thing I'm going to do, as we've discussed, is set the seed with np.random.seed. I'm going to set the seed as 42. I'll encourage you to do the same. If you know why I've set it as 42, that's great. If you don't, look it up. Now, remember we used a uniform distribution, then did some thresholding greater than or less than before. With the binomial distribution, we don't need to do that, okay? So remember, here, we're flipping a coin 10 times with P of heads equal to 0.7, okay? You do np.random dot binomial. Now, we haven't seen this function before. The first argument is the number of flips you want to do. We want to do 10. The second argument, positional argument, is the probability. So it's 0.7. Great. And we'll see that we got 8. And And if you set the seed the same as me, you should have got exactly the same. Okay. That's pretty cool, but we've only simulated it once, okay? So it tells us one potential outcome, but we want a distribution. So we want to see how likely it is to get n heads, for example. We've done it once, and we've got 8 heads. So, but maybe 7 was possible as well, and 9 and 6 and whatever. So to see how likely it is to get n heads, for example, we need to simulate a lot of times, right? And check what proportion of the simulations ended up with n heads, okay? So to do that, what we do is we do exactly the same as above. np.random.binomial 10.7. Now, this is a really cool thing about NumPy's random number generator. The next positional argument is the number of times I want to simulate this experiment that I've done here. I use the term experiment. I don't use that term lightly. I mean, we are using our, computational engine as an experimental lab of sorts in running these simulations, right? So it says simulate 1,000 runs. I'm gonna go do something wild and do 10,000 and see how that goes. Okay. Then we're going to plot a normalized histogram of results. The other thing I'll have you recognize is that this positional argument is very handy. If we'd done it like before, using the uniform distribution and then thresholding, you have to figure out something clever, probably for loops or a list comprehension or something like that to do that there. Whereas one argument here simulates it, well, I should say 10,000 times. Okay, great. Okay. Let's see. I think I got the number of bins wrong. Ugh. What if I wanted? Okay. Yep, that's exactly what I want. Okay, so what we see here is that over a quarter of the time we got 7 heads. Okay. Then a bit less of the time we got 8, 9. Ooh, is that right? Actually, we need to check our bin size here. Yeah, I'm sorry. This is 8, 9, 10. This is 7, 6, etc. Okay, so we've got a histogram of our results. And what I just want to make clear here is that in 2 lines of code, we've been able to model a data generating process, a very simplistic one, a biased coin flip. We've been able to simulate this experiment 10,000 times and plot the histogram, which I think is pretty cool. Okay, so now for a hands-on, what I'd like you to do is answer the following questions. If I flipped a biased coin with this probability 20 times, what's the probability of 5 or more heads? If I flip a fair coin 20 times, what's the probability of 5 or more heads? And then I want you to plot the normalized histogram of a number of heads of the following experiment, flipping a fair coin 10 times. And I want to give you 5 to 10 minutes to do this. I'll say the same thing in the chat to give me a thumb up when you've done it. And if you have any challenges, please do ask in Slack. What I'll get you to do is, if you've completed it, or you see a question that you think you know the answer to, I'd love for you to have a go at answering it. I'd encourage you to use threading in Slack. So if someone asks a question, you can click on the right on reply in thread. That's just a bit of Slack channel hygiene. That would be useful. No worries if not, though, to a certain extent. Alrighty, so we've got 14 people that have given me a thumb up. I'll wait for a few more, maybe a minute or two more. Once again, you can see my comment on Slack. Just give me one of those thumbs when you've completed the exercise as an emoji response. That would be fantastic. All right, that looks good to me, people. I'm also getting emojis coming through on AirMeet as well, which is, it's exciting. It's nice to see so much positivity as well. I'm just checking one thing. Okay, we're good. Okay, so I want to calculate the probability of 5 or more heads. Okay, right. So, what do I want to do? Once again, what's the data generating process? It's a binomial, right? So I want np.random.binomial. Okay, I'm flipping it 20 times, and the probability is 0.3. Now as above, I'm going to draw 10,000 samples. Now, I want to know how many of these are greater than, end up with 5 or more heads, okay? So once again, this gives us our array of booleans, which of trues and falses, which I'm going to sum up and divide by the number of samples, okay? So I got 0.7592, okay? So I'd be interested if people got something around the same, okay? If I flip a fair coin 20 times, what is the probability, okay? Just look at that as well. I mean, if I flip a fair coin 20 times, on average, I'll get 10 heads. I think a lot of the time I should get 5 or more heads. So what I need to do is change this code for the probability to 0.5. What I'm trying to kind of encourage us all to think of is kind of how modular the code is here as well, and how similar a lot of the code we're writing is. So if you go away from this part of the workshop, like going np.random.binomial, you know, that's a very good thing. Okay, yeah, it's 99.3 times, right? So flipping a fair coin 10 times, that's pretty much the same as this. That one was 20 times. I want to make it 10 times. And I want to plot the histogram, plt.hist x density is equal to true. And let's just say 10 bins. My binning in matplotlib leaves something to be desired occasionally. Okay, awesome. What do I want to say? Firstly, maybe I can ask you so we have a question in the chat in Slack, Sandeep. If I flip a fair coin 20 times, what is the probability of 5 or more heads? No, it shouldn't be near 0.5, right? Because if you flip a fair coin 20 times, you're going to get 5 or more heads on nearly all those runs, right? Because most of those runs you'll get around 10 heads, essentially. So what do I want to say here? Can anyone, I'm going to type this in Slack, tell me if this distribution looks like anything they know? That's poorly phrased. Does this distribution look like any distribution you've seen before? Okay. Yep. Awesome. Luca, you're amazing. So Luca wrote binomial. Now, of course, that's right. And as my question was leading, it really was what else can it look like? And the answer is it does kind of look Gaussian-esque, right? Now, there are several things about it that mean it definitively is not Gaussian, and I'll name 2 of them. But it does look unimodal. It has one peak and it looks symmetric, okay? So that's Gaussian, right? However, it has an upper limit of 10 and a lower limit of 0, okay? Normal distributions are not truncated like that. On top of that, it only takes on discrete values of 0, 1, 2, 3, all the way up to 10. Normal distributions are continuous distributions, okay? So that's something I've noted here, not quite that, but what I've noted is you may have noticed that the binomial distribution can take on only a finite number of values, whereas the uniform above, or the Gaussian, the normal one, can take on any number between 0 and 1 in the uniform case. These cases are different enough to warrant special mention. The former is called a probability mass function when we take on a finite number of values. The latter is a probability distribution function. We may discuss some of these subtleties I encourage you to check out Sevier and Skilling for more context, and any of Alan Downey's work on this stuff as well. I personally find fascinating. So I have a question for you. Looking at this histogram, can you tell me the probability of seeing 4 or more heads? And I don't want you to answer this. It's a leading question. And the answer is, it's kind of tough. If I was trying to figure out the probability of having 4 or more heads, I'd probably try to add up all these rectangles, but then I'd go, oh no, there are less rectangles below 4. So I'll try below 4. I've got like 0.1 something, 0.05. That's something. So maybe this plus that equals like, I don't know, 0.2. So then maybe 4 or above is like 0.8, or yeah, Edward has let me get out a ruler. That's brilliant. But that's the point, right? Like you can't really like read off stuff that you want to read off a histogram. Histograms are cool in some ways, and provide utility as to, to quickly visualize what a distribution looks like. There is the problem of binning bias. So, you could have a multimodal, a bimodal distribution and bin it such that it looks unimodal. So there are assumptions that go into this, and you can't read off stuff like this out of interest, okay? Great, and thanks, Carol, for Alan Downey's books. At Green Tea Press for that link. So I, as Alan does, and my good friend and who I developed these materials with, Eric Ma, we proselytized the wins of the empirical cumulative distribution function. That's a mouthful. It's an alternative to a histogram, which we're going to learn a lot about now and see why it's useful. It's a way to visual univariate data. So this is data with one variable, like we have here. And it's very rich in information. Firstly, there's no binning. It allows you to visualize all of your data, and thus avoids the very real problem of binning. It's cool because you can plot multiple different experiments, control plus an experiment, data plus a model, many populations. You can also see multimodality. You can read off so much, like percentiles, which you want to do a lot of the time. I'd encourage you to see Eric's great posts here. And this, I'd actually forgotten that I included a Twitter thread here. So let's just, okay, do not start looking at Twitter, Hugo. Yes, so this is actually a wonderful thread started by Alan, based on a tweet Eric wrote, based on a blog post Eric wrote about empirical cumulative distribution functions, which we're going to see now, okay? So let's jump in. Okay, so what is an empirical cumulative distribution function? An ECDF, the x-axis is the range of possible values, okay? Just like a histogram. Whereas the y value is, for any given x, the corresponding y value is the proportion of data points less than or equal to that x value. So you can kind of think of it as, for 4, it would be the sum of everything above it. So it would be the number of data points or proportion of data points less than or equal to that, okay? Because it's always less than or equal, it's going to be a monotonically increasing function or always increasing. So what we're going to do here is define a function that takes in data and outputs the x and y values for the ECDF, okay? So what we do is we compute the length of the data, then the x-axis, remember, is the range of possible values. So it's the data, and we want to sort it. We want to have it going from smallest to largest. And then the y is, as we said, for any given x, it's the proportion of data points less than or equal to that x value. So what we do here is essentially we're counting up the number of x values going up to there. So we're taking the range of 1 to n plus 1 and dividing by n. Then we're returning the x and y values. And we'll see what this looks like in a second. So what I want you to do now is to plot the ECDF for the previous hands-on exercise. Okay? And then what I want you to do is see if you can see from the ECDF the probability of seeing 4 or more heads, which we couldn't do super well from the histogram. Okay, so take a few minutes to do that. And once again, I'll put a note in Slack to give me. All right, everyone. Got a lot of thumbs, a lot of positivity coming on through. So we've generated our data set. What did we call it? X. Cool. So this is cool. This handy utility function, we can do ECDFX. Now, to plot it, I'm going to do plt.plot X flips on the x-axis, of course, y flips on the y-axis. Now I'm going to plot this. We're going to want another couple of arguments because this isn't going to look pretty, but I'm going to show you. Okay, so this is, we've got some sort of step function going up. We can't quite see what's happening. So the two things I'm going to do is set a marker so we can see the actual data points, right? And then I'm going to remove the lines. And you can decide to keep the lines if you want, but just know that what I'm plotting here essentially are the cumulative data points themselves. So line style equal to none. Okay, great. I just want to say, because of the thickness of the markers, we actually, it looks like at 5 it goes below what it is for 4, but that's just an artifact of the radius of the markers there. So essentially what we see here is that, so to answer the question, the probability of seeing 4 or more heads we can read off directly. The probability of less than 4 heads is just under 20%, right? So it's around 16 or whatever it is, right? So the probability of 4 or more heads is around just over 80, 84. And if we had more granular, more fine-grained labels on our axes, we could read it off completely. Similarly, the probability of 6 or more heads we see is 40%. We can read that off straight away. As I said before, other strengths of this are we could plot a lot of different experiments here as well. Controls plus experiments, different models, that type of stuff. Whereas as soon as you get to try to plot kind of histograms together, it gets really, really gnarly. We also have avoided the very serious problem of binning bias here also. Okay, so all of that's really cool. Now, before we kind of move back to probability, I do want to give a small aside on Monte Carlo simulations because they're incredibly important, and this part of the tutorial is about simulations. Monte Carlo methods, as I've quoted here from Wikipedia, are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. So I'm going to give 2 examples here, okay? So the first example, my background's in pure mathematics back in the day. So we're gonna estimate pi. This is quite a common first example for Monte Carlo simulations. So how do you even use simulation to estimate something like pi, right? So to do this, I want you to consider 2 shapes. The first one is a circle with radius 1 and center the origin in the Cartesian plane, x and y axes. The second is a square with the same diameter that goes around the circle, and we'll plot them in a second. I want you to notice 2 things. The area of the circle is pi. The area of the square is 4. Now this means that pi is equal to 4 times the area of the circle divided by the area of the square. And what I'm being told, I can see in the Slack. So Jonathan's written that the Monte Carlo simulations is not in the binder. Are you in the binder for SciPy 2021? Well, my binder went defunct. Binder times out for very good reasons. Are other people having the same issue? Okay. So if everybody looks at the screen I'm sharing and try to use threading in the Slack channel, if possible, we'll get there. Okay, so I'm going to notebooks, SciPy 2021, student probability. Moment of truth. And this doesn't, just a sec. So it is in mine. If you're looking at the instructor one, maybe it isn't there, but that's, that's what you'll get for cheating. No, I'm just kidding. That's fascinating though, if it isn't in the instructor one. Well, it is for me, so I'm going to move on. If you can't find it, my sincerest apologies. It's a brief interlude. You can consider it, an intermission break of sorts, if you'd like to. So great. The area of the square is 4. I'm actually just going to not look at Slack for a minute because it's frying my brain. The area of the square is 4. So this means that pi is equal to 4 times the area of the circle divided by the area of the square. Okay? Right. Area of a circle is pi. Area square is 4. So pi is 4 times the area of the circle, which is pi divided by the area of the square. Great. So if we randomly populate the square with points and then count what fraction of them are in the circle and then multiply the result by 4, we'll be able to approximate pi. So let's do it. So we're dropping pins in the square, dropping dots in it, and counting how many are in the circle. The way we're doing that, we're taking 1,000 points, right? Then dropping them using np.random.uniform. We're choosing an x coordinate for each point and a y coordinate. Because it's between -1 and 1, they all sit inside that square. Now, to see which ones lie in the circle, we look at whether x squared plus y squared is less than or equal to 1, okay? Then to count those, we sum them up, divide them by the total number, and for this algorithm, we multiply by 4, okay? So we do all of that. We get 3.192, which for the first 2 decimal places is an approximately pi. Sorry, to the first 1 decimal place, first 2 significant figures. So as we increase the number of points, let's see. Now this might get computationally a bit expensive. So this is as far as I'm going to go. So we're nearly at 3.14, okay? So you can increase this and keep going. You could speed up your code in a variety of ways. At some point, you could use something like Dask to parallelize if you're interested. That's by the by. Now, something for a bit of fun I just did here was turned this data into a data frame in order to plot it relatively easily. So, just to make sure. No! I plotted too many points. I'm just going to interrupt that. Okay, so this is the square, and then I look at the subset, which was the circle, and this is the circle. You see it doesn't quite look like a circle, it's slightly squashed because of the axes, but that's cool. So the next example I want to give before getting back to our probability distributions and storytelling, I think this provides a lot of interesting thoughts and ways to think about statistics as well. So this is from Nassim Taleb's book, Fooled by Randomness. And what he does here is he tells us to construct a Monte Carlo generator to construct a population of 10,000 fictional investment managers. And what we do is we assume that each has a perfectly fair game. Each one has a 50% probability of making $10,000 at the end of the year and a 50% probability of losing 10,000. So that's a biased coin flip. It's not even biased. It's a plain old coin flip, right? And what we see through this experiment, and this is a wonderful experiment in so many ways, is if you have enough investment managers doing coin flips and making and losing money on them, if you have enough of them, you'll see some that end up doing really well. Most of them disappear, but you'll see some that purely by chance end up doing really well. And that's hence why he called the book Fooled by Randomness, because the ones that by chance end up doing really well will then tell you all the tools and techniques they use to do really well, and will believe that these strategies are the strategies to do well in these games, quote unquote games. So in this case, we introduce an additional restriction. Once a manager has a single bad year, he's thrown out of the sample. So we're going to toss coins. Heads, the manager will make some money. Tails, he or she will lose. And so, as Taleb states here, at the end of the year, we expect half of them to be up, half to be down. Then we do it again, another half of the first half to be up, etc. So we'll only have a few left at the end, but they will have done very well. So what this code does here is essentially we're going through. Let me get this right. We start off with 10,000 I'm sorry, we're going through 10,000 time points exactly. We've got 10,000 fictional investment managers, and where for each of those points, for each of these investment managers, we're flipping 1,000 coins. So this is doing it over 1,000 different flips and investments. We're summing up all of them. So what we'll see is essentially a time series of the fluctuations. And what we're doing is we're throwing out all the ones that hit 0. So we have the requirement that for all t, x is greater than or equal to, we have the requirement that all t's are greater than 0. So if any of the investors hit 0 at any point, we throw them out. And then we plot them with some transparency because we're going to see a lot of them. I feel like the best explanation for this is to actually look at the figure, which we're about to do. So this is exactly what we see here. So there are a lot of investment managers who ended up down here, and we haven't plotted them because we're only plotting these requirements. But out of 10,000 investment managers, we can see loads that just by virtue of doing coin flips have done incredibly well. And we have an entire population, because we've started off with so many, that have actually survived in this random landscape, okay? And the point here, it's what's called survivorship bias, right? We're looking at the survivors. We're not looking at anybody who didn't do well. And in doing that, we've biased our sample to think of this as a population in itself. The reason I wanted to demonstrate this here, as I stated at the start, is because I think it's a kind of a wonderful example of the power of simulation and the tools that you've already learned in the last hour, okay? So after that detour into Monte Carlo simulation, I'd love now to jump back into probability distributions and their stories. Before going on, though, I just want to thank Justin Boyce, who's at Caltech, for countless hours of discussions, work, and collaboration on thinking about probability distributions and their stories. And all of what follows is inspired by Justin and his work, if not explicitly drawn from it. Okay, so above, we saw that we could match data generating processes with binary outcomes to the story of the binomial distribution, okay? So the binomial distribution story is as follows. The number R of successes in n Bernoulli trials with probability P of success, this is binomially distributed. So there are many other distributions with stories also. And I want to now tell you about one called the Poisson story, which gives us Poisson processes and the Poisson distribution. So David McKay tells the tale of a town called Poissonville, in which the buses have an odd schedule. Standing at a bus stop there, the amount of time you have to wait for a bus is totally independent of when the previous bus arrived. So this means you could watch a bus drive off and another one arrives almost at the same time, or you could be waiting for hours. This is called, the arrival of buses is what we call a Poisson process, okay? So essentially the timing of the next event is completely independent of when the previous one happened. And it just so happens that many real life processes behave in this way. One example is natural births in a given hospital. There is a well-defined average number of natural births per year, and the timing of one birth is independent of the timing of the previous one. The reason we have to be specific with respect to natural births is it is not the case with induced births, for example, because induced births are correlated due to the schedules of medical professionals who induce them. Other processes, landings on a website, Poisson processes, meteor strikes, molecular collisions in a gas, and aviation incidents, including many others. Now, the number of arrivals. So, to be clear, once again, any process that matches this story is called a Poisson process. Okay. So the number of arrivals of a Poisson process in a given amount of time is Poisson distributed. The Poisson distribution has one parameter, which is the average number of arrivals in a given length of time. So to match the story, we could consider the number of hits on a website in an hour with an average of 6 hits per hour. And this will be Poisson distributed, okay? So what I'm going to do is generate some samples, plot a histogram, okay? So np.random. Now, we've seen .binomial before, we've seen .uniform, and this is .Poisson, okay? To sample a Poisson distribution. Now, it has one parameter, the average number of arrivals in a given length of time, okay? So here, we have an average of 6 per hour. Parameter will be 6. And I'll draw a whole bunch of samples here. Let's say 10 to the 5. And then I'll plot the histogram. Samples. Okay, great. I just want a few more bins. I don't like my X labels. Well, I like that even less. Okay, so great. We've just matched a story to a Poisson distribution and drawn a bunch of samples and plotted it, once again in 2 lines of code, okay? So question is, does this look like anything to you? And maybe some of you say Gaussian-ish, maybe some will say binomial, and it kind of looks a bit like both, right? And the truth of the matter is the Poisson distribution is actually the limit of the binomial distribution for low probability of success and large number of trials. So that's for rare events. And I've given a brief explanation here as to why. I'm not going to go through that now. And if you're mathematically inclined, you go through the mathematics of these distributions and see that it's the case also. Having said all that, what I would love for you to do now is to plot the ECDF, take 2 or 3 minutes to plot the ECDF of the Poisson distributed data that you've generated above. Then what we're going to do is look at LeBron James's field goal attempts and see that they're Poisson distributed as well. So take a few minutes to do this exercise. And once again in Slack, I'll ask for a thumb up once you've completed the exercise. We have a great question from Itza. I hope I pronounced your name correctly, who asked in the previous exercise with investors, is this a 1D random walk? That's absolutely correct. And Prabhakar has asked, can I move up in the notebook displayed to show the previous code block? I can. Also go to the instructor notebooks because all the solutions are there as well. Okay, good. We're good to rock and or roll. So how do we do this before? ECDF samples, time to plot, plt.plot, x underscore p, y underscore p, marker, one style equals none. Okay. Cool. Okay, great. So we've got our ECDF as well. And once again, you can read off many quantities that you'd like to from here. And we're not going to do that now, though, because we get to move on to some really fun stuff, which is LeBron James's field goal attempts. Okay, so let's first remind ourselves of the story behind the Poisson distribution. The number of arrivals of a Poisson process in a given set time interval is Poisson distributed. So Justin said to me once, and I quoted this, we said it on the air actually, we could model field goal attempts in a basketball game using a Poisson distribution. When a player takes a shot, it's largely a stochastic process being influenced by all the ebbs and flows of a basketball game. Some players shoot more than others though, so there is a rate of shooting. So let's look at his LeBron's field goal attempts for 2018 NBA season. So this is the data which you can get from there. I've just encoded it in a Python list. So what I'm going to get you to do now is to show that LeBron's attempts are approximately Poisson distributed. You're going to plot the ECDF and compare it with the ECDF of the Poisson distribution that has the mean of the data. And if you're interested, the mean is also the maximum likelihood estimate. That's why we use that here. I'm going to get you started by, this first line of code is going to be the ECDF of FGA, field goal attempts. Now, I want to talk you through I'm not going to write this code yet, but talk you through it. What we're doing is we're going to plot the ECDF of the data. That's what we do here, okay? Now, we're going to simulate the model lots of times and plot the ECDF for each of those simulations. So we're going to do that 1,000 times, and then we plot the ECDF in a for loop, okay? 1,000 times. So we want to draw samples from the data. Now remember, we want, how do we draw samples from it? We're from the simulated data. The model we're simulating is a Poisson distribution. So we want np.random.Poisson. Now we need to tell it what the time the parameter is, right? And it will be the mean of this. Okay, so you need to calculate that and then decide how many samples for each sample, and it will be the length of this in particular. Then you'll construct the ECDF. So hopefully that gives you enough information to give it a go. Give it a whirl, and we'll then go through it together. I'm just putting in the Slack. Give me a thumb up when you've completed this exercise. Right, we've got 10 people completed. I'm going to wait till we get to 20, 25, something like that. Babak, you got it. It does generate some form of uncertainty plot, because what we're doing is we're simulating it many, many times and giving it a transparency. So the regions where it happens a lot more will have higher density of data points, right? Kyle has a great question. Is it statistically dubious to compare a model based on data with the data? Not necessarily, right? I mean, if you do it depends what you mean by compare. Like if you perform a linear regression, you're using the data to get your parameters, and then you look at it to see if the fit looks right to the eye. For example, we're not necessarily doing a statistical test here, right? So Kyle has asked, is it dubious to determine the distribution parameters from the data? Definitely not. Okay, so I'm going to write this and then answer Yelena's question as well. So, oh, this is fun. This is when things get fun, people, because it's 1:30 in the morning and the caffeine's kicking in. But what that means is that in about an hour and a half, the crash will come. np.random.poisson. Okay, what's the time? It's the mean of all the field goal attempts above, as we discussed, and the size, the number of data for each sample we want to draw, is the length. We want to kind of re-simulate LeBron's. We want to use NumPy to re-simulate LeBron James's field goal attempts. I don't know if I've ever phrased it like that, but it sounds like a real trip. And then we calculate the ECDF. Whoa. And then plot it, and we're plotting 1,000 times in this for loop, right? Let's execute that. Oh, that should just be len. Okay, great. So what we see here is these data points in the middle are the actual data, and all around it we see our simulations of the Poisson distribution. Okay, and we see that the actual data sits really nicely in our simulations, right? So what I want to say is you can see from the ECDF that LeBron's field goal attempts per game are approximately Poisson distributed. Yelena has a question. Does it make sense to do some kind of holdout data set here? You could, absolutely. That would be cool. But I think I want to speak to a broader question as well. Is like you could say, oh, what's the statistical significance? Yada, yada, yada. Do we want to do holdout? Do we want to do these techniques? Do we want to do that? And looking at this plot, we don't need to do anything, right? Like you can go away and calculate statistical significance because the editor of whatever journal you're submitting to wants or really requires that, and the peer reviewers do. But in the end, looking at this, it's Poisson distributed, and end of story. And in all honesty, when Newton developed his theory of gravitation and Kepler did what he did and Einstein did all his stuff, we weren't thinking about statistical significance and holdout sets. Robust theories, robust theories, and it's clear as day here. I wasn't comparing this plot to Einstein specifically, but it's clear as day here that this is approximately Poisson distributed for all intents and purposes, and that the Poisson distribution is a relatively good model for it. And it all depends on the question you're answering. As we'll actually see in the end, if you sample enough and enough and enough, it probably won't quite be Poisson distributed, but it depends on the question you're asking. There are some questions in Slack that I hope someone else in Slack will answer. I don't want to go through them now, particularly as these videos are being recorded, and the context for the people watching the video later without the context on Slack may not be super helpful. Okay, great. So now we get another distribution. Awesome. So we've encountered a variety of discrete distributions. There are also continuous distributions, like the exponential one and the normal or Gaussian one. We talked about the difference between probability mass functions and probability distributions functions before. So let's see what the story of the exponential distribution is. So to do that, let's return to Poissonville, in which the number of buses that will arrive per hour are Poisson distributed. But the waiting time between arrivals of a Poisson process are exponentially distributed, okay? So the exponential distribution has the following story. The waiting time between arrivals of a Poisson process are exponentially distributed, has a single parameter, the mean waiting time. The distribution is not peaked, and we'll see that from its probability distribution function. So as an example, we're going to check out the time between all incidents involving nuclear power since '74. Okay, it's reasonable to expect incidents to be somewhat well modeled by a Poisson process, which means the timing of one incident is independent of all others. If this is the case, the timing between incidents should be exponentially distributed. So just to start, to see if this story is credible, we can plot the ECDF of the data with the CDF that we get from an exponential distribution with the sole parameter, the mean, given by the mean time between incidents in the data. So what I'm going to do here, I'm going to load a data set of nuclear power accidents, then do some date-time conversion, and then look at the time between incidents, okay? And we don't need to worry about that, okay? I mean, we don't not need to worry about it, but that's kind of some boilerplate code that I really didn't want to get you to do so much. So we're going to calculate the mean of the intertimes, the times between events. So np.mean intertimes. Now we're going to sample from the population and plot the data and then plot the model. Okay, so I very much hope that if we're in a room and I said, what would the next word be here? What is the function we're using? We've seen np.random.Poisson. We've seen np.random.binomial. This will be np.random.exponential. Okay, there's one parameter, the mean, and I'm going to plot a bunch of them draw a bunch as before. So 10. Ooh. Into the 5, okay? Now, we're going to compute the ECDF for the sample into times. Yes, and we're going to plot it for the ECDF for the model as well. And I've overloaded the term sample here. And essentially, the samples, I'm going to actually call this model instead. Okay. So it's samples we're drawing from the model. Okay, we've done that. plt.plot. So this is the model. Okay. And look what we have. So this is the model and this is the data. And we'll see modulo a bit of variation, that the data is pretty close to being exponentially distributed, which means that, give or take, we can model the nuclear incidence as a Poisson process. Okay. Great. So what I want to do now is reintroduce the normal distribution, which most of you seem to know, the Gaussian, which appears everywhere. And there are many reasons for this. I think probably the most important reason is the central limit theorem, which is, so the point is that when you do repeated measurements, we expect them a lot of the time to be normally distributed because there are a lot of different sub-processes that contribute to a measurement. Why would these measurements turn out to be normally distributed? Well, because any quantity that emerges as the sum of a large number of sub-processes tends to be normally distributed, providing none of the sub-processes is too broadly distributed. So we're going to look at the example of measurements of the speed of light in the famous Michelson-Morley experiment. Okay, so what I'm going to do is plot the histogram with a Gaussian curve of the data. Sorry, histogram of the data with a Gaussian curve fitted to it. So let's just do that. Woohoo! Okay, that looks fine. But what does this actually tell us? I mean, the goodness of the fit could actually be due to binning bias, right? So what I want you to do is plot the ECDF of the data and the CDF, cumulative distribution function, of the model here. So what I've done is calculated the mean and standard deviation. Just one sec, Liz. I'm not sure what that... I'm sorry. Airmeet was telling my connection may be interrupted. I'm not sure if I dropped out, but it looks like I'm back now.
You are, Hugo. Your screen isn't being shared anymore.
Ah, okay. Thank you so much, Mike. I will make sure to share my screen now. Is it being shared yet, Mike?
No, not yet.
Okay, so what I'll actually, oh, it looks like, okay, great. I think we should be good now, or in a second. How's that?
I see it now.
Beautiful, thank you so much. Woohoo, thumbs up all.
So does everybody else.
Yeah, awesome. And apologies for keeping my file system open for so long. We've got more space here. I've calculated the mean and standard deviation of the data. What I want you to do is generate normal samples with that mean and standard deviation, then generate the ECDFs and plot them. Take 5 or 10 minutes to do this. We haven't seen what np.random.what to generate normal samples, but if you remember np.random.binomial, np.random.Poisson, np.random.exponential, and we want to generate normal now. I hope you can figure it out. So let's take 5 to 10 minutes to do this hands-on. All right, team. Let's do it. Okay. So I sincerely hope that some of you played around with np.random.normal, where we require two parameters, mean, which we've calculated, and standard deviation from the data. And you can play around with the number of data points. I'm going to take 10,000 here. Then I'm going to find the ECDF of the data. Then I'm going to find the ECDF of the model, or the theory, right? Wait a second. Samples. And then I'm going to plot the model. And I'm going to plot the data. And I'm plotting the model continuously, right? And I'll show you what that means in a second. But I'm plotting the data discretely. I'm plotting the actual data points as opposed to plotting a curve. Spelling gets tough after midnight. Okay, great. Cool. Okay, so this is our normal distribution, the ECDF, and this is the data. So we can see it looks approximately normal, which is good. So this is something I was hinting at before. Some of you may ask, is the data really normal? And I urge you to check out Alan Downey's post, which is called, Are Your Data Normal? Hint, no. And the truth of the matter is, once you have a large enough sample, it'll be very rare for your data to look normal or be statistically, or you'll get statistical significant differences from Gaussianness or normality. But does that matter? The answer most of the time is also no, depending on the question that you're asking and answering. So, in the interest of time, I'm going to skip the following section. This has been a whirlwind tour to using simulation and NumPy's random number generator to think about probability and data generating stories. Okay. The next section goes into how to think about joint probability and conditional probability using these techniques. But we're going to skip past that because we really want to make sure we get to the probabilistic programming and the Bayesian stuff. But I encourage you all to check out this section. All the solutions are in this instructor notebook. Feel free to ping me on Slack over the next couple of days as well, in this channel, for example. I suppose the one thing I do want to say is that, right, for those, just to have a refresher, joint probabilities, the probability of A and B is the probability of them both occurring, okay? If they're independent, then the probability of A and B is the probability of A times the probability of B, but this isn't always, and it isn't often, the case, okay? Now, conditional probability is the probability of A, something A knowing that some other B is true, and we use the notation P of A vertical bar B to denote this. So, for example, you can ask the question, what is the probability of a finch beak having depth less than 10, knowing that it's of species Fortis? So that's the probability of something being less than 10 given B that it's of a particular species, okay? And what I want to make clear is that there's a relationship between conditional and joint probabilities. So the probability of A times B is the probability of A given B, or A conditional on B, times the probability of B. Now, when they're independent, the probability of A given B, B doesn't affect A at all. So that's just the probability of A, in which case we get our formula from before that the probability of A and B is the probability of A times B. But more generally, we have this here. We have a conditional in there. So to give an example of where this will be useful, I want us to consider the case of drug testing, okay? So suppose that a test for using a particular drug has 99% sensitivity, so that's 99% true positive rate, okay? And 99% specificity, that's 99% true negative rate. So 1% false positives, 1% false negatives. I also want you to suppose that 0.5%, so that's 5 in 1,000 of people are users of the drug. Now, the question is, what is the probability that a randomly selected individual with a positive test uses the drug, okay? So it may seem that this is relatively easy to get out, but the challenge is we know that the probability, let me get this right. Yep, we know the probability that given someone is a user, that they'll test positive because we know what the true positive rate is. But what we really want to know is the probability of there being a user given a positive result, okay? So this is really an MVP, a minimal example for being able to move from the probability of the data given the model to the probability of the model given the data, okay? So the way we're going to do this first is computationally. But before doing so, perhaps you can everyone can put in, I'm just going to try to copy this here. I've posted the question in Slack. In the thread, would you mind just giving a sense of what you think the answer would be, if anyone feels comfortable? So if you know the answer, don't type it, or if you know, no spoilers, I think is what I'm trying to say. Yeah, so this is great. Jesse said 99%. Lucas said maybe around 10%. And there's such a wide range of possibilities here. And I think Jesse's response is very intuitive looking at it, because you see the true positive rate is 99%. So shouldn't, the other way kind of be similar there? And the truth is, in this case, that you'd think that would be true, but it isn't in this case, because the base rate is so low, because so few people actually use the drug. We'll actually see that base rate really impacts the probability of being a user given a positive test. And it's known as the base rate fallacy, actually. This is an example that really defies statistical intuition in a lot of respects, okay? So let's take 10,000, oh, no, this is 100,000 subjects. Okay, so the first thing we want to do is to, and I said this is a hands-on, but we'll do it together. We'll sample for the number of users and non-users. Okay, so how do we sample for the number of users? Well, how many are users? It's 5 in 1,000, right? So what we can do is, this essentially is a binomial story, right? It's a random coin flip where people are users with this particular rate. So np.random.binomial. There are n people in the sample, and we want to do it once. Now, we don't want to sample for non-users because we've already calculated the number of users. This will be n minus the number of users. Okay. How many tested positive? So once again, np.random, it's another binomial distribution. But now we're sampling the number of users, and the true positive rate is 0.99, okay? How many of the non-users tested positive? it'll be np.random.binomial non-users, and the false negative rate is 0.01. And so that's how we get the number of non-users who test positive, okay? Oh, I need to execute that cell first. Ooh. Great. So how many of these positive tests were for users? It's the number of users that tested positive over the total number that tested positive, okay? And what we see is it's around 31%, 31 to 32%, okay? So around a third. Oh, no, 33, I'm sorry. That's odd. Yep, that's absolutely right. So I would have initially been surprised at this answer, where, as I said before, we're experiencing the base rate fallacy. So the base rate of 99% true positive might lead you to think that most positive tests will be users, but the majority, the vast majority of the overall population of non-users, which means there will be more that test positive incorrectly than one would otherwise expect, right? So this is very much related to the serious challenge, scientific challenge posed at the beginning of this notebook. If you know the underlying parameters and models, you can figure out the distribution and the result, but often we only have the experimental result. We're trying to figure out the most appropriate model and parameters. It's Bayes' theorem that lets us move between these. And the second half of the tutorial is devoted to seeing how Bayes' theorem can be used for inference to go from data to model, okay? So Bayes' theorem tells us that the probability of B given A is the probability of A given B times the probability of B over the probability of A, okay? And you can derive that from this. We're not going to do that, but check it out in many places online. So essentially, if we substitute B for data and A for model, what we have here is the probability of the data given the model is the probability of the model given the data and another factor. And we'll see what all these terms are when we get to the second notebook, okay? Now, Bayes' theorem can be used to show exactly what happened here. And that's what I go through here. I won't go through that now. What I want us to do now, actually, what I'm going to do is, is open the second notebook and just tell you what we're going to cover in the second one. What we're going to do is understand Bayesian, the basics of moving parts of Bayesian inference, what priors, likelihoods, and posteriors are. We're going to use random sampling for parameter estimation to appreciate the relationship between sample size and the posterior. Then we're going to move into probabilistic programming for parameter estimation and hypothesis testing. Now what I'd like us to do is to take a 10-minute break. I'm going to stretch a little. I encourage everyone to do the same. I also want to remind everyone that a good break is one where we don't look at our phones as well. Of course, I'm not going to check on you if you do, but something I've learned is that if I don't look at my phone and I don't look at screens while I'm on a break, when I come back, I'm able to take in a lot more information as well. So let's take 10 minutes for a bio break, and I'll see you all back here in 10. Hey everyone, Hugh here. Hey everyone, Hugo here. We're back, ready to rock and roll. In Slack, Edward Kruger just posted a great link. Well, I haven't actually looked at the link yet. I'm looking at the title and subtitle, which I'm aware of. Study: most doctors flunk math of medical test accuracy, and I presume this is related to the fallacy I just showed in that final example when we're so I'm sharing my screen again. This particular example, how a lot of us intuitively would think that the answer is 90% or 99% or something along that, whereas actually it's closer to a third. Okay, and this isn't, you know, to cast any shade on doctors or medical students or anything like that. It's actually a huge problem with the lack of statistical intuition we have. There are facts of statistics that when it plays out, we've just done it with resampling, turns out to be the case that we as humans just do not have a good intuition for at all. So we need to be very aware of that. And Michael Clapp just made the point that it's very relevant in the age of COVID testing. I could not agree more. So spread the word of the base rate fallacy. And actually, of course, it has come up during COVID as well. I've seen it reported on explicitly. Okay, everyone, this is exciting. Now we're getting into the meat of things. Let's just import our packages. You'll see we're importing kind of the same things we did before. Sanja commented, but COVID is much more prevalent. I mean, the base rate fallacy occurs a lot of the time, independent of the actual numbers as well. You need a specific type of base rate, but it occurs. The base rate fallacy has occurred with COVID and COVID testing as well, along with vaccine efficacy. Okay, great. So as I said before, the learning objectives of this part are to understand what priors, likelihoods, and posteriors are, use some random sampling for parameter estimation to get a feel for that, and then dive into the wonderful world of probabilistic programming. Okay, so let's say we flipped a bias score. So this is to move from Bayes theorem to Bayesian inference, okay? Let's say we flipped a bias coin several times and we want to estimate the probability of heads from the number of heads we saw, okay? So statistical intuition tells us our best estimate is the number of heads of the probability is the number of heads divided by the total number of flips, okay? This doesn't tell us how certain we can be of the estimate, nor does it tell us, nor does this type of intuition extend to even slightly more complex examples, okay? So Bayesian inference will help us here. We can calculate the probability of a particular probability of heads. And I'm aware I'm overloading the term probability. We'll get to that in a second. So we can calculate the probability of getting a particular P given data by setting A in Bayes' theorem equal to P and B equal to data. So the probability of a particular probability of heads given the data is the probability of the data given that's lowercase probability times the probability of P divided by the probability of the data, okay? Now, this term seems a bit funny, and we'll get to that in a second, and we won't actually need that. But if you're wondering what the probability of data actually is, that's a very good question. Just 1 second. Okay, so in this equation, we call P of lowercase p the prior, P of D given P, the likelihood of the data given this lowercase p, and P of P given D, the posterior, okay? So I want to give you a bit of intuition behind this nomenclature, okay? So the prior is the distribution containing our knowledge about P prior to the introduction of the data. And the posterior is the distribution containing our knowledge about P after considering. And remember, posterior means after, so post-meridian, right? Post, after considering the data. So this is the posterior, that's the prior, As I stated, we're overloading the term probability here. In fact, we're using it in 3 different ways. We're referring to lowercase p, the probability of seeing a head when flipping a coin. We're calling the resulting binomial probability distribution, P of D given P, of seeing the data given P. And we're also referring to the prior and posterior as probability distributions of P, which encode our uncertainty about the value of P. So, something that is key, and I want to make clear, is that we only need to know the posterior up to multiplication by a constant at the moment, because we really only care about the values of the posterior relative to each other. For example, what is the most likely value? So to answer such questions, we only need to know what this thing is proportional to as a function of P. So that means we don't need to worry about the term P of D, okay? So the probability of P given D is proportional to the numerator here, the probability of D given P times the probability of P. Okay, so before jumping into some computation, I just want to say a quick word about the prior. This, for various historical reasons, is a point of controversy, whereas it doesn't really need to be with respect to Bayesian inference. So what is the prior? What do we know about P before we see any data? Well, as it's a probability, we know it's between 0 and 1. If we haven't flipped any coins yet, we don't know much else. So it seems logical that all values of P within this interval are equally likely, okay? So for example, that would be P of P is equal to 1 for all P between 0 and 1. This is known as an uninformative prior because it contains little information. There are also other informative priors that we'll get to, okay? But that's what we'll use here, and that's fine. People who like to cast shade on Bayesian stuff tend to claim the need to choose a prior makes Bayesian methods arbitrary. But as we'll now see, if you have enough data, the likelihood dominates. And remember, the likelihood was this term over the prior, and the latter doesn't matter so much. So something that's key to note is that this Bayesian inference helps us get out the whole distribution, probability distribution of the posterior, not merely a point estimate plus error bars, okay? So what I want to do now is actually do some parameter estimation and flipping some coins, okay? Now, we're going to generate some coin flips and try to estimate the probability of heads, okay? So you'll never do this in practice, but this is purely for pedagogical purposes. So given data D consisting of n coin tosses and k heads, this is the likelihood function, okay? It's a binomial of some sort. I don't want to go into really what it is now, but I tell you that because that's what I'm going to use here to plot the posterior. So first we're going to set the seed. Then we're going to flip some coins. So the default arguments for this function are probability 0.6 and 0 flips, and we can, it's a function, right? So we can put anything in there. Of course, we want the number of flips to be non-negative. I can hear someone else's computer, I think. I don't know. Okay. So n successes is equal to np dot random, and I hope you're all thinking it has to be binomial. np. Now the x-axis, it's the probability, right? So it's going to be, I'm just going to create equally spaced labels, array between 0 and 1, 100 of them. Now the prior, remember, is going to be equal to 1. That's what we kind of decided here. Now the posterior, I'm just going to copy and paste this. So it's x to the power of n successes times 1 minus x to the power of n minus n successes. And that actually, I'm so sorry, this here should actually be n minus k there. Okay. So this is the likelihood, and you get the posterior by multiplying it by the prior, and I'm just normalizing the posterior here. Okay, so the peak is at 1. So what I want to do is create that function and then plot a posterior for p. I'm going to set p is equal to, leave p equal to the default 0.6 and do it for 10 data points. Okay, so what we see is that at this point, right, so the posterior is telling us possible values of p, and we see 0.6 is kind of likely. With what we've done, 7 is more likely. So for these 10 coin flips, we probably got seven heads, right? And then we see it go down there. So I'm just going back to the Slack channel to... Oh yeah, thanks everyone for posting about 42. Great question. And that's an amazing image, Mike, that you just posted as well, or that is in the Wikipedia page. Okay, so now one of my favorite things in Python land completely is what we can do now is we can use an SciPy widget to vary n and p. Okay, so we're going to use the interact widget, and this should work in Binder as well. It did for me earlier today. So I'm going to plot the posterior. I pass interact the function I want to plot, and then I want to tell what type of values I want to be able to give it. So p, I want to be able to give it values between 0 and 1. And let's say I want gradations of 0.01. And then n is equal to, I want to go from 0 to 1500. And I want it to go in steps of 1, and that's the default here. Okay? So look what we have here. We now have the posterior, given p is equal to 0.6 and n is equal to 0. So what I'm going to do is I'm going to increase n slowly. I'm going to flip a coin. And look at that. Look at what the posterior looks like now. So you can tell that I must have flipped ahead, because the probability of it being totally biased towards tails is 0. And we have a linear probability function there. Let's flip it again. Okay, great. Must have got a tails there. Okay, I'm going to keep flipping. And we see, as we generate more and more data, the posterior becomes narrower and narrower. Okay? And I encourage you all to play around with this. So let's say the probability was really low. Okay, great. The other thing I want to mention is you need more data to be certain of your estimate when it's when your actual probability is in the middle, as opposed to when it's at the edges. And think about it. If the probability of getting heads is really high, all you need is, if you flip it 10 times and you mostly get heads, then you're like, oh, okay, that's probably pretty high. Whereas if it's in the middle, you're going to get data on either side. So I encourage you all to play around with that SciPy widget a lot more as well. So now I want to talk about the choice of the prior. So you may have noticed that we needed to choose a prior. And in the small to medium data limit, so we have a question: why do we want the peak to be 1 instead of the sum of PDF to be 1? Yeah, you could want the integral, the area under the curve, to be 1. That's harder to calculate. So, but I did it equal to 1, essentially because we only care about the shape and the values relative to each other, essentially. So as I wrote in detail and mentioned up here, we only really care of the posterior up to multiplication by a constant. If you want to plot the actual probability distribution function, definitely do make sure the integral is equal to 1, or the sum under the curve, okay? So in choosing a prior, in a small to medium data limit, the choice can affect the posterior. We've seen that. So we do want to discuss it briefly. I'm briefly going to introduce several types of priors, and you'll use one of them to see the effect of the prior. So firstly, there are informative priors. And these express specific, definite information about a variable. So if we got a coin from the mint, right, we may use as an informative prior a peak at p is equal to 0.5 and small variance, okay, because we're pretty sure it'll be a fair coin. Weakly informative priors express partial information about a variable, such as a peak at 0.5 with a larger variance, right? Uninformative priors express no information about a variable except what we know for sure, such as knowing that p is between 0 and 1. So now things get a bit bizarre. So you may think that the uniform distribution is uninformative, okay? However, what if I'm thinking about this question in terms of the probability, and my collaborator Eric is thinking about in terms of the odds ratio, R, which is P over 1 minus P. Eric rightly feels that he has no prior knowledge as to what this R is, and thus chooses the uniform prior on R. So with a bit of algebra, you can show that the uniform prior on P amounts to choosing a non-uniform prior on R and vice versa. So Eric and I, in choosing uniform priors on different variables using the same philosophy, have actually chosen different priors. So how do we avoid this? We use something called the Jeffreys prior, which is an uninformative prior that solves this problem. You can read more about the prior here and in your favorite Bayesian textbook. Sivia gives a nice treatment. So in the binomial coin flip case, the Jeffreys prior is given by this function here. And so as a hands-on, I want you to create, I'm just wondering whether I want you to do this, or I'll give you a few minutes to do it. Create an interactive plot like the one above, one for the uniform prior. So it has two posteriors, one for the uniform, another for the Jeffreys. So what I'm going to do, and suggest you do, is to copy and paste that there and edit it. So let's just go through the way I'd want you to do that. Actually, no, I'm not going to get you to do that because I think in the interest of time, we want to move on to PyMC3. What I'm going to do is I'm going to copy and paste the solution from the instructor notebook, and I'm going to post it in Slack as well. There's the solution in Slack. And I'll also post it in AirMeet. I don't know if AirMeet likes Markdown or code cells, but okay, that didn't quite work, but we're good. Just upvoted myself. I'm going to undo my own upvote. Hubris. Okay, so we've executed that cell. And then we're going to form an interactive plot again. So look at this. When we have no data, this is a Jeffreys prior and that's a uniform prior. So the prior deeply impacts the posterior, right? When we have no data. So let's start generating data. Well, that's cool. So we've generated like 5 data points, and they're not exactly the same, but they're not like, they're not wildly divergent. And look at this. As soon as we get to, 30 data points, the uniform, the choice of the prior doesn't really impact the posterior at all. Okay. So I've asked the question here, which I've just answered. What happens to the posteriors as we generate more and more data? And what happens is they get closer and closer. Awesome. Okay. So now we get into the meat of Bayesian parameter estimation using probabilistic programming and PyMC3. Okay. So I just want to take a beat for a second and congratulate everyone. So well done. You've learned the basics of Bayesian model building, okay? The steps are to completely specify the model in terms of probability distribution. So this includes specifying what form of the sampling distribution, what form the sampling distribution of the data is, and what form describes our uncertainty in the unknown parameters, okay? Now, this formulation is adapted from Chris Fonsbeck's workshop, as Chris said it really well there, and I encourage you to check it out. Then step 2 is calculate the posterior distribution. Helena has a question. We have one parameter to estimate here. Can it happen that we have many, and then the amount of data we need becomes too much for realistic estimations? We're going to see examples where we have more that we need, and we'll see that we need more data to do that. But I mean, in the end, if you have a huge space, perhaps the data is too much. But in essence, then perhaps you need a simpler model. Okay, great. So, in the above, the form of the sampling distribution of the data was binomial, okay? And the uncertainty around the unknown parameter was captured by the prior, okay? Now, there's a third step that we won't cover today that you can look through some of the other notebooks for, which is called performing posterior predictive checks. What this means is making sure your model actually makes sense. So you can look through several other notebooks on this. So what I'm really excited to show you now is how to do this using the probabilistic programming language, PyMC3. There's loads about PyMC3 and this paradigm, loads to learn, and loads of good stuff. And 2 of the most important things are that probability distributions are first-class citizens. What I mean by that is that we can assign them to variables and use them intuitively to mirror how we think about priors, likelihoods, and posteriors. Okay, so similarly to, in Pandas, data frames are first-class citizens. In scikit-learn, your models are first-class citizens. In NumPy, your arrays are first-class citizens. In PyMC3, distributions, probability, are first-class citizens. On top of this, PyMC3 calculates the posteriors for us, okay? So under the hood, you don't necessarily need to worry about this. PyMC3 will compute the posterior using an approach, a sampling-based approach called Markov chain Monte Carlo, or it will use variational inference. You can check out the docs for more on these. But now it's time to bust out some MCMC, Markov chain Monte Carlo, and get sampling for our posteriors. So let's go through a small example. Okay. So a common experiment in tech, in data science, is to test a product change to see how it affects a metric you're interested in. So say I don't think enough people are clicking on a button on my website, and I think it's because the button is a similar color to the background of the page. Then I can set up another page and send some people to that and some people to the original one. And the only change is that the button is of high contrast or something like that. Okay, so this is commonly referred to as an A/B test. I actually think that the math and simulation of this is interesting, but I'm just, A/B tests are just so banal these days. You can probably hear the boredom in my voice, but when we get to the actual computation, that's when the fun stuff happens. This is commonly referred to as an A/B test, and the metric of interest is click-through rate. The other thing that frustrates me about A/B tests is that you get very small incremental changes like this, and it's all based on data. It's not based on, hey, why don't we try to think about like large-scale changes? We're creeping up like local optima in A/B tests, as opposed to thinking, what does my point is that when Steve Jobs came up with the iPhone, that wasn't the result of an A/B test on a normal phone, right? We want to make big leaps some of the time, right? And if we're doing just these constant incremental changes, oh my. Anyway, enough technological philosophy here. So this is commonly referred to as an A/B test. The metric of interest is a click-through rate. But before looking at two rates, let's just use PyMC3 to estimate one, okay? So what I'm going to do here is I want to generate some data, okay? So we've got 150 people visiting a website. Click-through rate is 0.15. So I want to generate, the question is how many people did it. So click through, so np.random. Binomial and P of A, and I just want to make sure that great. Okay, that looks about right. Okay, it's a bit more than you'd expect. It's actually what happens if it was 0.2, but that's fine. It's random sampling. So now it's time for us to build our probability model. Okay, so we've got this data, right? So our model of having a constant click-through rate is a biased coin flip. So the sampling distribution, remember we need two things. We need the sampling distribution of the data and what form our uncertainty, what form describes our uncertainty, okay? So the sampling distribution is binomial, and we need to encode this in the likelihood. There is a single parameter P that we need to describe the uncertainty around using a prior, and we'll use the uniform prior for this. These are the ingredients for the model. So let's build it, okay? So we use something called a context manager, okay? So with pm.model as model, okay? So in here, we want to set the probability. This is the prior. We want it to be a uniform prior. So note that this is kind of like our NumPy random, like we write out the name of the distribution we want. That's on the variable P. Okay. Now the binomial likelihood, PM dot binomial. The variable is Y. Now, what data do we want to give it? We want to give it the number of the sample size, which is uppercase N. Now, we want to tell it what the prior for P was. Just a sec. As we saw in this example, let me get this right. Yep. So we want to tell it how to describe the uncertainty around P. Okay. And we want to tell it about the data we've observed. So the observed data is N successes underscore A. Okay. And this is how we build our model, right? So while that's executing, usually I'd have a discussion around what we think of the API for PyMC3. Or what I'll say is that I think it's really nice how it reflects the way that we think about building the model. Okay, so within the context of the model, we say what the uncertainty is with respect to the prior. Then we say what the sampling distribution is and describe it in terms of everything we've been discussing so far. Okay, which I think is very powerful. So we've built the model, but now we kind of want to know about the posterior. And we'll do this using PyMC3. So we'll sample from the posterior, and then we'll plot it. So actually, I'm going to create a new cell to plot it here. So what I want to do is, once again, in the context of the model, I want to sample from it, right? So the posterior. So PM. So I'm sorry, I didn't mention we imported PyMC3 as PM, so that's the PM dot. I hope that is clear now if it wasn't before. And let's sample 2,000 samples to get a sense of what the distribution looks like. So what it actually does is it jumps around the posterior distribution and samples it in order to kind of show us what the distribution will look like. And as a rule of thumb, start with 2,000 and see what it looks like. So it's telling us some details. It's using a no U-turn sampler and doing a bunch of chains, and you can look up the details of everything that means. Okay, great. I'm just looking at a question. It looks like I almost disconnected again. Mike, am I still here?
You lost your presentation window.
Great. I'll start sharing it again while I answer the question that you, thank you for posting in Slack from Ryan. If we can say, given enough data, the choice of the prior isn't too significant, can we conversely use a rely? I don't quite understand that old, sorry, I'm just trying to share my screen as well. Can we?
Your screen is back up.
Great. Can we use something on a weakly informed prior with few data points? I don't quite understand that question, unfortunately, at the moment. But if someone wants to repost it, we can chat about it. Okay, so this code has run. Let's not worry about these. These are non-issues. In all honesty. Okay, great. So what we have here is the posterior distribution, and we'll see that it has a mean of 0.2, which, great. So we saw 150 samples, 30 of them were ones, and so that is actually 20%. So that's as expected here. And we see the highest posterior density, which is, we can expect, by some definition of expect, 94% of the data to lie between 0.1 and 0.3. Not of the data, I'm sorry. We can have around 94% confidence that our variable lies between 0.1 and 0.3. Okay. So moving on. What I want to do now, having done this, I'd like you to code out a parameter estimation, the mean of population, okay? So I'm going to get you to load in the data set of the finch beaks. And I want to remind you that to specify the full probability model, you need a likelihood function for the data and priors for all unknowns. So what is the likelihood here? So I'm just going to plot the data here, and it's approximately Gaussian. There's something happening here. So I'll encourage you to use a normal likelihood. The unknowns here are the mean, mu, and standard deviation, and I'd like you to use weakly informative priors on both. A normal prior for mu with mean 10 and standard deviation 5. A uniform prior for sigma bounded between 0 and 10. So we can discuss biological reasons for these priors, but you can also test that the posteriors are relatively robust to the choice of prior here due to the amount of data. So I want to give you 5 minutes or so to have a go at this, and then we'll jump into the hypothesis testing, and then we'll wrap up. I might just give some little hints here. All right, let's take one more minute. Okay, everyone. We've had a couple of people complete it. I appreciate. We've had perhaps at least a small step function in kind of cognitive load and difficulty of these hands-ons. So I want to jump in and do this. So PM dot, we said it will be a normal prior. Okay, it's called mu1. That's how we name it. And, well, I said mu is equal to 10. Standard deviation is equal to 5. Then for this, I said it will be a uniform prior on the standard deviation. I'm copying and pasting that. Uniform between 0 and 10. Okay. Now the likelihood we said above would be Gaussian, normal. So it's going to be PM dot normal Y1. Then I want to specify the uncertainty, of course. And here, the uncertainty around the standard deviation is given by sigma 1. Once again, remember, we want to give our observations. We want to see what our data actually was for our likelihood, of course. And this is this. So we're now building that model, which will take a second. And as before, the sampling is the same as before. PM dot sample PM. So that will take a tick now. And we see here, these are our posteriors, right? Posteriors for mu1 and sigma 1, okay? The mean and the standard deviation came out. So what I want to get into now is the hypothesis testing. We've done our parameter estimation for click-through rate and the mean of the beak length. Now it's time for hypothesis testing, okay? So this is the A/B test we were talking about before. So I've got one click-through rate is 0.15, one is 0.2, sample size 1,000, and I'm just going to generate the number of successes for both of these, okay? Done. So once again, we need to specify our models for the probability of A and probability of B. Each will be the same as the click-through rate examples above. So binomial likelihoods and uniform priors on PA and PB, okay? We also want to calculate the posterior of the difference PA minus PB. And we do so using something called PyMC3 PM.deterministic, which specifies a deterministic random variable. So this one is completely determined by the values it references, in which are these two, okay? So it isn't probabilistic on top of those probabilities, essentially. So we're getting used to this. So with PM.model, as model, probability of A is PM.uniform, uniform distribution, and we have PA there. We've got PM.uniform PB. Now, the binomial likelihood is PM.binomial. First up, we have our YA. So this is the same API we've been using. We've got the sample size. We've got our prior on PA, and we have our observed, our data. With n successes underscore A. Okay. Now I'm just going to copy and paste this because the next line is very similar, except all the A's will be changed to B's. And then the diff clicks is PM dot deterministic. It's diff clicks, and it's the probability of A, as we have up here, minus the probability of B. And this is our model, fully specifying the binomial likelihoods and the uniform priors on both, okay? Okay, so I need to express these quarks correctly. So once again, we're going to sample. Great, so that has run. Now we're going to plot the posteriors. Okay, cool. So we have the posterior for P of A, and the posterior for P of B, and the difference now. This, let me think. Actually, I'm going to look into this once you start doing the hands-on. Actually, let me just check one thing. the challenge that's happening here is that they're not both the same, but they're rounding up to decimal places. So I'm actually, like, to clarify, the problem I'm having here is the mean here is like 0.15, but it's rounding to 0.2, and the mean here is 0.2. So I just round to. Okay. Okay, beautiful. So we see the mean here is 0.15 or thereabouts. Here it's 0.2, and the diff is 0.04. Now, the reason it's cool to plot the diff is because we can see the confidence intervals around the diff, okay? So what you can actually see is that it's incredibly unlikely that the difference is zero. 94% chance that it's between this and this, okay? So if you go to, remember, this is an A/B test, your growth team manager or your marketing guru or whatever, and you're like, look, it's most likely the difference is 0.05, but it could be here, could be here. I can say it's between these two, definitely not zero. So there is some form of change. They can say, this is good enough for me, let's implement the change, or they can say, let's go and collect more data to actually get a bit more confidence around what the difference actually is. Great. So what I'd like you to do now is to take 5-10 minutes to do the Bayesian hypothesis testing to beak lengths difference between species. And what I'll do, see how far you get. This is a bit challenging. You can do most of it given what we've done, but give it a go. And in 5-10 minutes, I'll come and show you my solution as well. And after that, we'll wrap up. And then, as I said, if you want to go through all the joint and conditional probability stuff in your own time, I can answer any questions about it on Slack. All right, everyone. I'm back for the final frontier. Okay. So what I'm actually going to do is copy and paste it from the instructor notebook and paste it in the Slack channel as well, the solution. And then talk you through it. Okay. So let me execute this and then, ooh. Oh, curious. I didn't copy the entire thing. I need to add a little bit to that code chunk. I'm just doing this in Slack as well. Okay, cool. So what's happening here? We have priors for our means and variances. These are exactly the same as we did before in the parameter estimation mean of a population, okay? Then we have our Gaussian likelihoods, which are exactly the same as before also. After this, we have the difference in means, which is deterministic. Now, as we did before in the previous example, we also, to calculate the effect size, and I don't want to go into too many details here, but as I mentioned here, it's the difference between the means divided by the pooled standard deviations, okay? But I want to talk, I want to talk about the importance of effect size. Essentially, we may see that, you know, there is a difference, but the difference may not be that large. And in frequentist statistical hypothesis testing, you may see a statistical significance, but is it actually significant? You want to know how big the actual effect is, right? And the units of the effect size should be in terms of standard deviations of other parameters. Because if you have a large standard deviation, or if you have an effect size that is around the standard deviation, that effect may not be super real due to the fluctuations with respect to the standard deviation. Okay, great. So we use our PM.deterministic to get this pooled standard deviation and then the effect size. Now I'm going to sample, and I'm just going to check one thing while we're waiting for that to happen. Okay, great. Now we're going to plot the posterior, all the posteriors, and we'll see we have mu1, big size mean 10.5. Then 13.4, mu2, then the difference in the means, and once again, the effect size. And we see the effect size is incredibly large in terms, so having something which is 5 standard deviations or 5 pooled standard deviations different is incredibly large. Great. Okay, well, look, I'd love to thank you all for joining once again. Any questions you have, feel free to post in this channel, and any questions about the extra, if you go and finish notebook 1, please post in this channel as well. I very much appreciate you all joining. Once again, I want to thank SciPy for joining. And if there are any questions that you think maybe more relevant to the material as a whole, please go to the GitHub repository and raise some issues. Also, that would be super cool. I also hope you all have a fantastic rest of your SciPy. And thank you all once again.
Thanks very much, Hugo. I know it's really late for you, so we appreciate you putting in the effort to stay up really, really late, or super, super early. Okay, with that, I think I will end the session, which will be the end of the recording. So you can continue to post questions on the Slack channel, and Hugo can hopefully answer those as he has time this week. Again, thanks very much, everybody.